Hello everyone, welcome to the next video of our Lab 5 where we are trying to integrate interrupt in our zynq SOC system. So as discussed in our block diagram design, so in our block diagram we have enabled the interrupt from the DMA MM to S as well as S to MM transfer, and we have connected this to the zynq SOC on the corresponding interrupt port. Now we need to understand how we can enable the interrupt in our application code so that we know when the interrupt is generated and what action should be taken after the interrupt is generated. So we will start with our Lab4 code where we had two functions where we were comparing the performance of the ACP and as well as HP port. So I have removed the HP port comparison because we are not using that port. And in the ACP port comparison, I have added the subscript POL to indicate that this is the we are using the polling mode. What is the polling mode? We will discuss it in the next few minutes. So this function is same as the function which we use for the ACP port comparison in the last lab, except the name change. So in this mode, you can see that whenever we transfer whenever we ask the DMA to perform the transfer of data, we wait and we keep on reading the status register of the DMA from the particular set of address. And this is called as a polling mode. What do you mean by polling mode? Here we are continuously reading the status of the register to know whether the DMA has completed the transfer or not. And this reading operation leads to the AXI read transaction, and which takes a significant amount of time, and that's why the DMA execution time of the 8.50 is very high. Now what we try to do is that instead of polling the status register, we ask the DMA to generate the interrupt whenever the transfer is complete, and whenever that interrupt is generated, we will do the subsequent necessary task. Okay, and this is how we are going to use the interrupt. So in this code, it is used as a polling mode, and then we will write another code for the interrupt. Now to begin with, we will copy the same code as it is with the few changes we need to do. Okay, so there are three main changes we need to do from the polling mode to the interrupt mode. Okay, so this is the code for the interrupt mode. It is exactly similar to the polling code, which is this code which we use in the previous lab, with the three main changes. The first main changes is that we will write a separate function to enable the interrupt system. We have already discussed in our first video what is this interrupt system in the zynq SOC and what are the 6 to 7 steps which we need to do to enable the interrupt. So that we are going to do it in the setup interrupt, and in this one what we are going to pass. Now in the interrupt system we need a interrupt controller. So for that we are going to create the corresponding instance, so that we are going to pass. Then the source of the interrupt, which is the DMA, which we are going to pass, and the ID of the interrupt, because there are two types of interrupts are generated. They will have the separate ID. So those we are going to pass. Where these IDs are located, again they are located in the xparameter.h file. So you can see that 61 and 62 are the IDs of the interrupt. So by using these IDs, we are able to differentiate which interrupt is generated by the DMA, because same DMA is generating both the interrupt. So this DMA instance structure, you are already aware about it. Similarly, there will be structure for the interrupt, which we will discuss it when we will discuss the interrupt system. So this is the one where we are enabling the interrupt, and we are telling the ARM processor what should we do when the DMA generates a particular interrupt. Okay. Now this DMA generates the interrupt in the three scenarios. For example, when the transfer is completed. Second, when there is some delay issue in the transfer, or when there is a error in the transfer. So based upon that, the different types of interrupt will be generated, and what we will do in the interrupt handling, that we will generate the local flags to indicate what has happened after the interrupt has been generated, and we will make use of the flag to indicate to the user that whether the DMA transfer is successful or not. Then the rest of the code is same. We will do the FFT on the PS. We'll find out the execution time. FFT on the PL. Here we are just going to do the simple transfer. We are going to tell the DMA to perform the simple transfer. After the transfer is done, DMA will enable the interrupt. DMA will generate the interrupt. That interrupt will be processed by our application code in that setup interrupt routine function. We will write it that later. And based upon that, the interrupts function will set up this flag. And through this flag, we will know whether the transfer is completed or not. So we will wait for the this one of the flags to go 1, because by default these flags values are 0. So once this flag goes, one of the flag goes high, then we will say if there is an error condition or not. If there is no error condition, then we are good to go. We have completed the one experiment. If there is error condition, we will display that and we'll break the corresponding experiment. Then what we will do, once the experiment is successful, we will compare the output of the FFT on the PS and output of the FFT on PL like we did in the previous lab. And the last step, after we do the printing, we can also disconnect the interrupt system in case we want to do it. Okay, this is again optional step, but it is always good to disconnect the interrupt system after we completed the operation. So overall, compared to our Lab4 code, there are 3 changes, main changes. One, we need to write a code for setting up the interrupt system for every source of the interrupt. Second is that we need to generate a local flag so that we know that the corresponding transfer is completed, and we need to disable the interrupt. So now we will start with the discussion on the setting up the interrupt system. This process is exactly same as we discussed in our lab video. So in the setting up the interrupt system, you can see that we have the our interrupt controller. For that, we will create the instance, and for that we need to add the .h file. So your scugic.h file is used for the interrupt handler. So we can open that one. And you can see that this is the generic interrupt controller driver component. So as we see in the zynq SoC, there is a interrupt controller is there. To make use of this, again, we need to use the structure. Again, there will be 2 structures. One is the configuration structure and one is the normal driver instance. So you can see that I have created the corresponding driver instance. I have kept it as a global because we might have to use it in the multiple functions. And then the structure, I have kept it as a local. So if you look at this one, I have kept it as a local one. Okay. So 2 structures has been generated. Again, same as the DMA, we'll do the lookup config and config initialize. So process is same for any IP we want to use it. Then as discussed in the video, first thing we need to do is that we need to initialize the exception handling unit in the ARM processor. Okay, so we can call this function. But if you look at this function, it is an empty function. So because by default, this exception handling unit has been enabled in the Cortex A9. But in future, if you use some other processor, you need to enable it. So that's why it is good to use this as a call. You can call this one so that the code can be used for any other processor. Okay. Now we have enabled the initialize the exception handling unit on the ARM processor. Now, when the interrupt happens, there are some initial tasks need to be done so that the corresponding interrupt can be processed in the proper manner. So Xilinx has provided its own general interrupt handler. Okay. What we need to do, we need to register that handler. Okay. With our, and we need to tell that handler that this is our generic interrupt handler which we are going to use in our code. Okay, so this is our instance of the generic interrupt handler, and this is the Xilinx provided exception handler. So whenever the interrupt is generated, you can see that the ARM processor will ask this GIC interrupt handler to find out the source from which the interrupt has been generated, which in turn will ask this GIC to find out which is the source of the interrupt handler. Okay, so that's why this is the second step we need to take care. Okay, so we can go into this function, and you will see that It is nothing but it is copying the information of our GIC instance in our in the vector table of your processor. Okay, so you can also look into the corresponding description. What it say, it register a handler for specific exception. This handler is being called when the processor encountered the specific exception. In the processor, there will be multiple source of exception, like for example, interrupt may happen, divide by 0, wrong instruction, and all those things. But now by using this, we are telling the processor that if you get any interrupt, you make sure that you check for this interrupt controller instance for the source of the interrupt. Okay, so this is very important, and there is a corresponding ID is given to this ID is important because you can see that the this ID is used in the proper entry in the table. Okay, so exception ID contains the ID of the exception source, like our interrupt controller, and should be in the range of the 0 to corresponding range. Okay, and where this ID is there, so you can see that this ID is there in the corresponding exception.h, and this is the IRQ interrupt ID. Okay, so and this ID is again a 5U. Okay, so that means there are two types of interrupt, IRQ and the FRQ, which we'll discuss in the theory. But now whenever the ARM processor gets the IRQ request, it will ask the corresponding interrupt handler to find out who is the source of the interrupt. Now this interrupt handler will look at his vector table, and then we'll find out, okay, this is the general interrupt controller which is aware about the source of the interrupt, because that his entry is there, his name is there in that vector table. Now this guy, we need to tell this general interrupt controller to about the source of the interrupt. Now we have two sources of the interrupt. So this is the connect function is used. This connect function, which is our general interrupt controller, this is the ID of the interrupt. There are two IDs of the interrupt, which I'll discuss it in few minutes. And then we are telling the this interrupt controller that if you receive the interrupt from this ID, you should execute this function. Okay. Now this ID again, this is the one which we have passed from our C code. Okay, here, and this ID is again there in the our x parameter.h file. So these are the IDs which are there. So by looking at this ID, we will know from in the DMA, since there are two interrupts are generated from the DMA, which source has generated the interrupt. Okay, so from this, what we are telling our general interrupt controller that you will receive the interrupt from this ID. If you receive the interrupt from this ID, you should execute this function. This is nothing but the ISR, interrupt service routine, which we need to write. This is a user specified ISR, so we need to write it. And this is the callback reference function. Okay, this is the callback. So let's go to the one. Here you can see that it makes the connection between the interrupt ID of the interrupt source, okay, and the associated handler that is to be run when the interrupt is recognized. That is, whenever the corresponding interrupt happens, what should be done? The argument provided in this call is a callback reference, which is used as an argument to the handler, that is interrupt service routine, when it is called. So here you can see that what we are saying, whenever the interrupt comes from this source, execute this function. But it may happen that we may use this function for the multiple interrupt source. So inside the handler, if you want to know who is the source of the interrupt, then we can use this callback reference for identifying from where this source has been executed, from where this corresponding interrupt has been generated. Okay, so this is the correct function. Since we have the two interrupt, we'll repeat the same thing for both the interrupt. After this is done, then we need to enable the interrupt on the GIC side, interrupt controller side. Also, we need to enable it from the source side. The switches we need to close it, and we need to repeat it for both the interrupt. This is the optional step where you can set the priority of the interrupt. It is the optional step. We can look at what it is doing. Okay, so this is the sets the interrupt priority and trigger type for the specified IRQ source. For example, your trigger type can be age trigger, level trigger. So those can be set. We'll keep it as a default as possible. And also you can give the priority. You can give the highest priority as well as the lowest. Avoid the highest priority because those are specified for the some specific important exception as well as interrupt. So here we have given the uh, uh, the priority. We will check it out. What is the priority we have given? So the priority we have given as the 3. No, A0 we have given the priority. Again, it's a number which is mentioned by the Xilinx. And then the type we have mentioned is the. So just give me 1 minute. Yeah, so the we are mentioning it as a rising age sensitive type. Okay, so you can give the corresponding priority. Then in the enable one, it is just writing to the particular set of register. That's what it will do. You can see that it will write to the register. What it does, it's enable the interrupt source provided as a argument interrupt ID. Okay, so that is what it does. Similarly, it will do it same for the DMA. On the DMA side, it will enable the interrupt. Okay, is the enables the interrupt specified by the mask in the direction as well as it will you specify the mask as well as the direction. I'll discuss that one. So in this case, only those interrupts will be generated. Now you can see that the DMA can generate 3 types of interrupt. One is the completion interrupt. Second is the delay interrupt. Okay, and third is the error interrupt. So in this case, by using all masks, you can see 7 means all the bits are 1, right? 1, 4, and 1, 2, and 4. All means we are enabling all the 3 interrupt. If you don't want all the 3 interrupt, you can choose one of them. Okay, and if you want to know more about this, you should look into the DMA dataset. Now we are enabling all the interrupt for both the MM2S and S2MM. And then at the end, we are enabling the interrupt in the ARM. So now ARM processor can start receiving the request. Okay. So we have set up the interrupt request in our code. Now the final step we need to do, we need to we have told the interrupt handler that interrupt controller that you should execute this function when the interrupt happens. So we need to tell what should be done. Again, this is the user specified function. We can write whatever we want. I'll give you the example what we have done in our code. So in our code, what we are doing, whenever the interrupt happens, this function will be called. Whenever the S2MM interrupt is happening, this function is called. Like here, whenever the FFT sends the process data to the DMA, this function will be called. It's a S2MM. Then what we are going to do, using the callback function, we are going to copy all the information in our local instance of the DMA. Okay, then we are going to check what are the interrupts has been generated, whether it's a completion, delay, or the error interrupt. And then we are going to acknowledge the interrupt. That means we are telling the DMA IP that okay, I have received your interrupt, I have copied all the data. Now you can close that interrupt, you can reset that bit, and you can start receiving the next set of interrupt. Then we are checking whether the DMA has generated the error interrupt. So what we are going to see, we are going to AND this with the first thing we are going to see is that whether there is any interrupt has been generated. As I told you before, this function can be used for the multiple source of the interrupt. Okay, right now we are using only for the S2MM interrupt, but it can be used for the multiple source of interrupt. So we are using this callback function. We are just checking whether the interrupt has been generated by the particular DMA or not. Okay, if it is not generated, we will just skip this function. If it is generated, then we will see whether the error has been generated. By using the error mask, we will see that the particular bit has been set to 1 in the IRQ schedule. If this bit is 1, that means the transfer is completed, but there is an error. If the error happens in the DMA transfer, we need to reset the DMA. So we'll use the reset function. We'll reset the DMA. Sometimes reset doesn't happen in one go, so you need to wait for the reset to happen. You can use the while loop like this. Then if the error is not generated, interrupt has been generated, but there is no error, that means our S2MM transmission is done. We will generate a local flag. This will be used in our main function. Same function can be used for the MM2SS. There is no change. Only thing is we are doing is that we are setting up the M2SS done function, where rest of the things will remain the same. Okay, so this is how we have completed our interrupt handling in our ARM processor. And now we will test our function. So you can see that in our code, after the interrupt has been processed, we will get these flags which are generated by the interrupt service routine, and we'll check those flags in our code to just see that whether the transmission in the both the sides of the DMA is completed or not. Now what we are going to do, we are going to verify the functionality of our two function, one with interrupt, one is the without interrupt. We are going to check them. Okay, so what we are going to do is that I'm going to run my code on my remote hardware. So debug configuration. Okay, so I'll program the processor and FPGA. Okay, so I'll start my JTAG terminal, and then I'll run the code. So in this code, you can see that both the polling mode as well as the normal mode, interrupt mode has been completed. In the polling mode, as we discussed in the previous lab, the processor is 2.82 microsecond, FPGA takes 4.75, and because of the interrupt mode, you can see that we have reduced the time for the ACP mode to 2.6. So you can see that now the FFT via ACP mode. ACP mode is faster than the FFT on the PS for the 8-point FFT. Okay, so that's the advantage of the interrupt. Interrupts are the very important part of the embedded system, and you should make sure that you understand this concept and make use of them efficiently in your design. Here we have seen the small example of the interrupt and how they are generated. Now what we are going to do is that let's go back to the ILA, because we have used the ILA here, and what we are going to do is that we are going to see whether we can see the interrupts which are generated by the processor. Okay, so what I'm going to do is that I'm going to add the trigger on this one, on the one of the interrupt output, and I'm going to observe whether we get any trigger or not. So I'm going to use only basic trigger because that should be sufficient. And I have not enabled the cross triggering because I don't want to do it. Okay, I need to first, I need to first do the configuration and then set the trigger. Okay, so debug configuration. So since the FPGA gets programmed again, your trigger will be lost here. So you need to again run the trigger again here. Okay, so you can see that your trigger is lost. So now I'll run it again. Now it is waiting for the trigger. Okay, so I'll just run it here once. Okay, so the trigger has been captured, and now you can see that the trigger is generated. So you can see that the two types of interrupts has been generated. MM to S, that is from the DMA to FFT, and S to MM from the FFT to the DMA. So you can see that both the trigger has been generated, and you can see that because after the transfer from the DMA to the FFT, and before the transfer before the data from the FFT to the DMA, you can see that there are no GP0 transaction. You can see that we are saving a lot of time in between on the GP0 transaction, and that's the advantage we get. What we will do is that we will now look into the non-DMA mode, a non-interrupt mode like polling mode, and we'll see what is the difference in the timing diagram we get. So yeah, so I'll do the debug. Again, the FPGA will be programmed so that we will lose out on the trigger we have set. So I'll remove this trigger now. And what I'll do is that I'll put the trigger on the GP port, the read transaction. Okay, so in the read transaction, I think AR1 is the better one, AR valid, and we'll put it on the 0 to 1 on the AR valid. Okay. Okay, so I have now 0 to 1 transfer, 0 to 1 transition. So let's wait for the trigger, and I'll run the trigger again here. Okay, the trigger has been captured, and let's look at the timing diagram one more time. So here you can see that okay, so I think we got the trigger in the beginning of the transfer, but not when the data is being passed. So what we'll do is that we'll run it again so that we get the trigger in the middle when we are doing the transfer. So I'll run it again. So what I'll do is that I'll enter into that polling code, and I'll just go to that time before we do the simple transfer, so that we'll get the exact point of the data where we want to see the transaction between the on the GP port. So okay, so what I'm going to do is that I'm going to do the simple transfer, and yeah, so then I'll now start the trigger here. So let's hope that we get something in here. Okay, we got some data here. Yeah, so I think I got what I wanted. Yeah, so now you can see here the data is being passed to FFT, and here the data from the FFT is being passed to the DMA, and between them you can see that there are so many transactions are happening, and this is happening because of your polling mode, and because of this our FFT takes so much time to execute, because these are the transactions which are happening. Because of the interrupt mode, you will see that the this space is empty. Okay, so that's the advantage of the polling mode. So now I think we have already seen it in the previous simulation, but I'll do it one more time. I'll show you the what happens now when we go to the interrupt mode. Okay, so instead of putting the here, I'll just remove this trigger, and I'll put the trigger on the one of the signal. Okay, 0 to 1 transaction, and I'll do this one, and then I'll run the code. Okay, and now here you can see same code. Now you can see there is nothing is happening between the FFT data is being passed to the FFT and data is received from the FFT, and that's where we get the speed up in the execution time, because you are saving the read from the status register. So this completes our lab on the improvement in the FFT acceleration via use of the interrupt in the zynq SoC.